Great, thank you so much. Welcome to the session where we'll be covering campus decarbonization planning. We are very fortunate to have three excellent speakers discussing their own campus decarbonization planning efforts. First up, we're going to have Gerry Hamilton to discuss Stanford's decarbonization journey. Then Kira Stoll will describe UC Berkeley's vision for a clean energy campus. And then Brian Pratt will give us an overview of UC Irvine's plans for an all-electric hospital. How's that sound? Okay, on to the logistics. We're going to have each speaker present for about 20 minutes. Maybe we'll cut that down to 19 minutes so we can get everything back on session. That'll leave us with 20 minutes for questions from you throughout the session. We'll cover all of the questions together. So as you hear from the speakers, please type your questions into the chat. We'll be moderating those. The chat's enabled, so you can feel free to connect with others as well as we do the presentation. Okay, first up, we have Gerry Hamilton, who is a key leader within Stanford University Sustainability and Energy Management team. Gerry's responsible for long-term energy use planning. He designs and implements energy management programs. He oversees business systems and analytics initiatives, and he leads Stanford's smart building technology deployment. He graduated from Santa Clara University with a BS in mechanical engineering and an MBA. Nice to see you, Gerry.
Thank you, David.
Looking forward to hearing from you.
Well, why don't we get started here? I've got to get to the home. So it's a privilege to be here. I'm honored to go first with this great panel team. And let me jump into Stanford's decarbonization journey. We've come a long ways. We've still got a lot of work to do, but it's good to take time to reflect and kind of celebrate the wins as we go. I think most of you have heard of Stanford. Here's some quick facts. Probably for this presentation, I'll draw your attention to the energy numbers down here at the bottom. It's important to point out that Stanford University operates a district heating and cooling facility, a central energy plant. We have had district heating and cooling for decades. I'm going to get into more detail here, but in 2015, we switched from a natural gas-fired cogeneration facility to a new one, and I'll get into those details. And we switched from steam distribution to heating distribution, but you can see some of our peak numbers down there. Let's see here, we will continue. So I'm jumping right into our greenhouse gas emission chart. This is what we call our wedge chart, and I'm only showing you half of it right now. It's a little teaser. Each of these wedges are the various components in our scope 1 and scope 2 emissions. Without getting into all the weeds, the big bands are what you would expect, electricity and natural gas combustion on site. And my role is primarily on the demand side, and so we run new construction and energy retrofit projects, and these dashed lines up here on the top show the impacts of those programs. And so we definitely moved the curve, but if you look at the big picture, we're not doing much, right? And so that's kind of a bummer. But what else can we do, sort of thing. If we go back to about 2008, the university was in the middle of a major campus-wide sustainability planning exercise. All the schools, all the departments, we had working groups on water and waste and transportation, and obviously climate and energy. Ultimately, climate and energy seem to get the most attention. They got the most budget, but certainly we had great impacts in other areas. But in 2008, the forecast more or less aligned with what actually happened here. And the question was, well, Gerry, demand side's great, but we got to do a lot more. And what are we going to do? And by the way, this campus is growing, both in terms of square footage and the energy intensity of that square footage. And so where do we go? Well, some great ideas came about. We made some great implementation work and ended up with this. These numbers are actually updated about through 2021. Great success. We basically exceeded our goals, and now we've got new goals. But for the rest of my time here, I'm going to tell you a little bit about what happened here going into 2015 and how we made this possible. Little background, I do have to plug the fact that we have been doing energy efficiency work since the 70s. In 1993, we had our first formal budgeting mechanism for operation expense type projects. In 2004, we implemented a formal capital expense type program, and great results, great savings, great cost effectiveness, comparable to what many folks participating today are familiar with. Other milestones: in 2001, we published our guidelines for sustainable buildings. This was a new construction document. Our first energy and climate plan was published about 2010. We've had a few versions of that. We're working on a brand new one now. Significant fleet electrification began about 2011, and we've got most of that complete now. Some big challenges still remaining to complete. But the big thing that really made that step change happen was our Stanford Energy Systems Innovation project. And we've spoken a lot about that. Many of you on this call probably heard bits and pieces about it. But I want to focus on the greenhouse gas aspect of this and some of the decision making that went around that. So again, jump back to about the 2008 timeframe. The university was considering, what do we do with an aging cogen facility? It was old. It needed significant capital renewal work. In fact, we were just kind of keeping some things together with duct tape and baling wire until we could make the ultimate capital decision. So something had to happen. This was wasn't kind of a retrofit ROI type approach. It was like, we got to do something, and what's the best present value option going to be for us? Obviously, we were in the middle of planning our sustainability goals. So how are we going to support a bold vision? And the university also wanted to expend its resources responsibly. We didn't want this to be a pet project. We're throwing money at it. We want to do the right thing. And Stanford's fortunate that we can look out towards like a 30-year horizon, right? And the university does have access to capital, but still that present value has got to make sense. So jumping ahead, what was the big aha moment here? We looked at our energy balance coming out of our central energy facility, and basically we plotted on an hourly basis for a typical year how much energy is going out in the form of chilled water and how much is going out in the form of steam or heating energy. And when you plot that, you end up with a graph like this. The blue lines, the vertical bars go up, that's chilled water load, and the red bars go down, that's heating load. And then you compare the two, and we realized we had about 70% overlap in terms of heating energy and cooling energy. And the obvious question was, can we pull the waste BTUs out of the chilled water that's being returned to our plant and somehow pump it up to a useful heating temperature? And to cut to the chase, yes, that was the answer. Yes, we could. We ended up proceeding with some new heat recovery chillers. We got a little photo here. We got 3 of those, and they make this magically possible. We're able to take that waste heat, and so big energy savings, big carbon reduction there. I want to take just a second here to comment on some of the dialogue that was happening back as late as 2010 and maybe even 2011, and we had many groups of the faculty involved. We had actually some very senior mechanical engineering staff, and they said, well, electrification, that's great, but at the time, most of the majority of the power in the California grid was coming from gas combined cycle. And if we're going to use electricity, wouldn't it be more responsible for us to generate it locally? And if we're going to burn any gas at all on campus, shouldn't we at first try to make some electricity with that? And so that was a big hurdle that we had to get past before we could electrify. It seems kind of different to think about now, but back then that was a big decision. But 2 things came through. One, the Graduate School of Business said, you know what, I don't recommend being tied into natural gas solely for the next 30 years, basically all your energy coming from that. Electrification gives you a little bit more flexibility in terms of procuring the source of that electricity. And if in the future we can get to a point where we're getting renewable electricity, well, then it's a no-brainer. Yeah, we should electrify. And that's what enabled us to move forward. highlights of what our project entailed. Well, the end result is we had about 90% electrification of our heating needs. Over any given year, about 90% of our total BTUs are coming from waste heat recovery. We still have to burn some natural gas to make up the balance in winter, but that's a huge step change for us. We saw a lot of efficiency improvements in general. A big co-benefit was eliminating the steam distribution system because it had a lot of losses. The new hot water system has very little. We had some significant water benefits. Since we don't have to evaporate as much waste heat from the cooling system to the atmosphere, we're not evaporating as much water. We use about 75% less water in the new plant. I mentioned we had 3 heat recovery chillers. Of course, we have a large conventional chiller plant with evaporative cooling towers. We get probably less than 45% of our annual chilled water load from the heat recovery chillers. We're a cooling dominated campus, and our cooling load is only growing, which is a topic for another seminar, but we are seeing that. We put in a lot of thermal energy storage, both chilled water and hot water. That helps us with obviously load flattening, but also it gives us a little bit more flexibility on how we operate our assets. We can kind of run them at their sweet spots. We don't have to swing them as much because the storage can take up a lot of the variability. In addition to a new plant, we had to put in all new underground distribution piping for hot water. We had to modify 155 building mechanical rooms. And so each of these was its own major effort. The one thing that we actually did that was original, thermal energy storage, not original. We weren't the first campus to use heat recovery chillers, but we did develop a model predictive control software tool that originally we called Central Plant Optimization Model. It was developed originally in-house and it was patented to be used to right-size the plant. Now that the plant's built, we kind of know what it is, but before it was built, how many pieces of equipment do you use? What size? Do you use boilers and chillers? Do you use heat recovery? Do you put in some internal combustion engines? How much storage do you use? And you model that over, an 8760 hourly year and end up doing lots of Monte Carlo simulation. So that is new, and now we use it as a dispatch tool for optimum operation of the plant. Better to be lucky than good. Around 2012-ish, I can't remember the exact time. I know Sam Zimmerman's on the panel or the call here somewhere, but he could probably tell us he's our PG&E contact. The market opened up for direct access, and Stanford applied for that, and we succeeded in acquiring direct access, which meant we could go to the market and procure our commodity as we chose. And PG&E is still getting the power to us, but we can now procure the portfolio. That enabled us to take advantage of a rapidly changing and improving renewable generation market. And that unfolded much faster than we anticipated, but it validated the recommendation we got from the Graduate School of Business, which was, hey, let's give ourselves some flexibility with our electric procurement. Around 2016, we had both an on-site and an off-site solar PPA project come online. SSGS, that stands for Stanford Solar Generation Station. So the first one came online, and then we had another one come online, number 2, early this year. And when that plant came online, we can technically say that 100% of the kilowatt hours we're procuring come with RECs that we're generating ourselves. The new plant actually came with about 100 megawatt hours of battery for us. There's several off-takers, so we get to share the big facilities down here on the bottom right. So now the task for us is, okay, now how do we match our actual load with renewable production? So we want to go beyond just kind of the RECs component and helping get the community really aligned with demand and production. Here's a figure we use a lot. It's kind of where are we at on our greenhouse gas reduction journey. This is scope 1 and 2. Again, over here on the left, we've completed SESI. We worked our way up here, and we're acquiring, green electricity. We've still got some fleet work to do. Our buses are pretty much electrified, but we still got, utility trucks and these big awkward vehicles we've got to figure out what to do with. Still have some facility conversion work to do in our hospitals to get them tied on to our new hot water system, and then all the odds and ends of cooking equipment and peripheral buildings that aren't tied into our central plant yet or can't be, and how do we deal with that electrical load? So my demand side management team has a lot of work to do going ahead. We kind of call it the last 10%. How are we going to do this? This is the hard part, but it's also exciting. And then, of course, task 3 is big. We have a major initiative around that, another great topic for the future. And what I want to lead you with here is there's so much more research we can do on the building side. We want to get our smart buildings smarter. We want to be able to integrate them with our central energy facility optimization model. That means we need to have much more potent hourly level building forecast models for electricity, chilled water, and hot water. We need to be able to manage, model that, have the models update themselves, autocorrect so that we can get the humans out of the loop, make them more reliable. We need to be able to model demand management measures, not just DR, but what can we be doing on a day-to-day basis to deal with our own demand peaks related to hot water and chilled water, and be able to model that so we can make confident dispatch decisions. And it's no longer just about efficiency. There's several drivers. I invite you all, when we're done here, to do a little Googling. Google cooler at Stanford. I put a link in here, but you guys aren't gonna be able to, I don't think, click on that. But the cooler program was a 3-summer program we did with a research team from multiple schools, actually. And then we had faculty, not just grad students, but faculty, grad students, undergrads, and we did some basic, simple research. And it was so simple, we didn't even think of doing it until we actually started talking and trying to integrate with our academic partners. All we were doing is doing bulk set point changes in multiple buildings to all the rooms at once, and then monitoring the impact. Now, obviously, in summer, if you increase the set points, you're going to have a favorable reduction in chilled water demand. But how much? What does that curve look like? What does it look like on a 75-degree day versus an 85 versus a 95? If you do it in hour 1, what's the impact in hour 12? What's the impact in hour 20? Because we have a lot of storage. We're managing our energy kind of on a 24, 48-hour basis. And so what's it mean to save a peak chilled water ton hour? Because that peak ton hour was generated a long time ago. So we're going to have a paper out on this early in the coming calendar year. But it's been a great success with this joint collaboration. It gave meaningful deliverables to operation and provided real meaningful research for the academic team. And now we're trying to figure out how to bottle this success. You know, neither party was a burden to the other. So how did we stumble into this? And so I think we'll be talking about the cooler program in future presentations as well. And with that, David, I think I should probably wrap up so we can get others moving here.
Great. Thank you, Gerry. Really appreciate it. I should just note what a great partner Stanford and Gerry have been to UC on our journey, and all of higher ed as being one of the early adopters for campus decarbonization efforts. So thank you, Gerry. Next up, we're going to hear from Kira Stoll. Kira is UC Berkeley's Chief Sustainability and Carbon Solutions Officer. How's that for a title? One of her key initiatives is the Berkeley Clean Energy Campus, which you're going to be hearing about today, which has the goal to transform the campus into an electrified and renewable energy microgrid to reduce campus carbon emissions by 80% and model the transition to 100% clean energy on the scale of a medium-sized city. Kira, the floor is yours. We don't hear you yet, Kira.
Thank you. Good morning. Thank you for having me, and what a great turnout to this event. So I'm really pleased to be here today to share with you where the UC Berkeley campus is in this decarbonization journey. Gerry's presentation is inspiring. It's an operating system, and what I'm going to talk to you about today is Berkeley's journey, where we're at right now in terms of visioning the direction we want to go, and how we're starting our transition into implementation of moving away from fossil fuels, electrifying the campus, and using a variety of other tools and techniques to make our microgrid renewable. So just a little bit of context for the Berkeley campus. For those that aren't familiar, we are located in the city of Berkeley in the San Francisco Bay Area. Our main campus park is about 176 acres. That main campus is currently served by a natural gas cogeneration plant that's almost an antique. It was 1987, and it provides steam for heating and for lab processes, and the electricity provides about 2/3 of the electricity that we use on the main campus, or about 12 million square feet right now. The electrical grid that we have on campus, we own and operate the grid on the campus. PG&E brings in power to the top of the hill, to stations that we have there, and then we distribute that to the campus. So that electrical grid serves the main campus, as well as some of the buildings that we have on the hill and some of our peripheral buildings, particularly housing that we have and buildings that we have just adjacent to the main park. So just kind of a setting there of what we're trying to do. We're a large campus, about 55,000 people on the campus on a busy day. We have more gross square feet, but what we're looking at doing right now with our decarbonization project, at least in the initial phases, is taking care of about 12 million of that square feet. So why now? A little bit similar themes running through here. As I said, we have an old system. We have steam infrastructure that's a lot older than the cogeneration plant. We have boilers that we use in the cogeneration plant. I think one of them is 1950s vintage. And we're looking at the end of life for that system in about 5 or 10 years. So we're motivated by needing to do infrastructure improvements and being able to, have the campus around for another 150 years and make this investment at least for the next 50 years. And also obviously motivated by our goals to decarbonize the emissions. So for perspective today, from a carbon standpoint, you can see on that graph to the right, we emit about 130,000 metric tons of CO2 a year from that plant. We're regulated by cap and trade. And what we are aiming to do by decommissioning the cogeneration plant over time and moving to a new system is to take those emission levels below California's cap and trade threshold of 25,000 tons or more. But that is the target that we're looking at now. So what's been our journey? We've been talking about this for a long time. When I started in the sustainability office in 2008, we were already talking about what are we going to do next with the cogeneration plant, kind of knowing that that it was going to reach end of life and was going to need some significant investment. In 2015, we really started the journey of looking at what the alternatives are. So since 2015, we have done 3 technical plans. We've studied, I put 12 plus system options up there, but we probably started with about 40 and whittled it down to about 12 that we studied. In 2015, we were still very much looking at, what were the, as we were looking at cost models and we were looking at what we thought was feasible, we were still mostly looking at gas solutions for the future. Do we rebuild the plant? Do we go back onto all utility electricity? Do we just put boilers in? Do we keep the steam up? Do we move to hot water? All of these kinds of questions that institutions were asking. Following, and in 2015, we also looked deeply in that study about what energy efficiency would look like and how much we would have to kind of do transformation of energy efficiency in the buildings. As time went on, We updated the studies again in 2019 and then again in 2020, where we started narrowing down our alternatives. And about 3 years ago, we really were able to pivot and say, our journey is going to move us away from fossil fuels, and we should really only be looking at electrified solutions for our thermal systems. And so we then kind of, again, whittled it. How do we do this? How do we do this in phases? Do we do it in a more distributed mode with several plants on campus? Or do we look at one centralized plant, and did some evaluation on that? The other part of our planning process, as we were doing these technical energy planning processes, the campus was going through a process of doing a long-range development plan and a new environmental impact report and a master planning process. And so we were able to fold in these concepts of a new plant and a new infrastructure system into that planning, which is kind of helping us set the stage of being able to move forward and having some of that evaluation done already. So what have we landed on? So what we've landed on is moving to a electrified thermal heating and cooling plant for the campus, moving to hot water away from steam. We're looking at a centralized plant model with an ability to build the plant and phase in equipment over time as we're able to do distribution to the campus. We're starting to look at how we replace the resiliency that we have with that current plant and the microgrid that we have with it on there. I will say that in parallel to this, there's a lot of electrical upgrades that need to be done. We predict our electrical needs will double as we electrify our thermal systems. And so there's been work going on with PG&E in terms of do they have will they be able to provide that level of power to us? Are we going to have to, at what juncture of our phase in of this new system, are we going to have to maybe expand the substation we have, the main substation we have? We're already looking at additional smaller substations on campus that we're going to have to put in, new duct banks. We're almost at our electrical capacity right now, so we know this work has to be done, but it's also a huge component of what we're having to do. So this is it's a very wordy slide, but we really just wanted to kind of capture what our goals and objectives are around the carbon and the energy and the resiliency. And so, part of our, discussions we've had with the state is about a public sector institution of our size, medium-sized city. How do we make that transition? How do we take a microgrid that's reliant on fossil fuel and transition it? And then how do we integrate other kinds of technologies into it to create the resiliency and hopefully grid benefit as well from that? We know that we need to maintain our resiliency and our independence. Easier said than done, and it was good to see from Stanford too that's the last mile, or the last piece. It's quite challenging. But we're also looking at how many other benefits we're going to get from this project. We are going to be tearing up the campus to run new piping. It's an opportunity to build back better. It's an opportunity to improve our ADA pathways. It's an opportunity to take care of what we're roughly estimating about $100 million in deferred maintenance while we're at the project. And we're also looking at things like running new non-potable water piping while we have it. So our goal ultimately is to have zero carbon energy to our campus buildings by 2035 or sooner, and maintain the microgrid and the resiliency that we have in place. So just in summary, we're looking at all kinds of solutions for the resiliency. We've begun looking at possibilities for larger solar arrays on site in our Hill campus. Where does battery storage fit in? We're looking at some geothermal heat exchange opportunities, and we know that we need advanced building controls That's kind of where we're focusing a lot of the efficiency, really being able to manage our buildings in a much better way than we do now. A lot of the systems are quite manual. We have different control systems on different buildings. And just for perspective, there's about at least 100 buildings that we need to connect to this new system. And then we're open. We've got to look at fuel cells. We've got to look at green hydrogen, whatever those might be, and be able to piece those into the future. And again, we are looking at opportunities for a water reuse facility on campus, and also in discussions with our local water utility about recycled water options for us. Again, this is about people. It's more than just a technical solution. So we have commitments around retaining all of the full-time jobs that we have on campus, retraining staff. We know that we're going to be generating, jobs during this construction over a number of years and contributing back to the California economy. We want to improve public health in our area, taking out a gas powered plant will benefit the local air pollution, and we want to enhance the campus as a community resiliency opportunity. Lots of engagement, and this is a big project. It involves a lot of people, and it also involves fortunate that we're at a university that we have so much knowledge and experience to tap into. So there's been a lot of work around engaging and getting feedback and working with faculty on teaching and learning opportunities and living labs. And we've seen a real surge in excitement around this, kind of activating some research, applied research, grants, going in for grants together, a variety of things. And I've highlighted here, if you have a chance, their engineering professor on campus, Kenichi Soga, is really kind of a good example of our living lab opportunities. He applied for a student green fund grant and did organized drilling a 400-foot borehole to test our soils for geothermal heat exchange potential. He's using that data to teach an undergraduate course, and he has graduate students and postdocs to doing the analysis. And we've just submitted a DOE grant together to further explore the geothermal exchange. So finally, where are we today? We are still planning. We are in what we call a integrated resource and activation planning phase right now. It was donor funded, this piece of it. So we started seeing some excitement from the donor philanthropy community around what we were doing, and they helped us kickstart this process that we're in right now. So this process is including another technical study, much more in depth, that includes reviews, going into 60 of our buildings. What is it going to look like to change those out? It's, looking at how do we build out the central plant? How can we phase in? Where do the cooling towers go? What can we do with the cogeneration plant that we have now? How do we step it down? Can it be used for emergency? There's a lot of questions out there, which we're excited to get the answers to over the next couple months. And along with that, we brought on a financial consultant that's going to help us do some financial modeling once we get the costing updated from the technical studies. Very conceptual budget is about $700 million. This is not a small undertaking. We don't have all of this financing in place, so we are still building off of that. And, roughly we think about half of the cost will be the core thermal system and half will be microgrid and resiliency. We were really fortunate this last year. We took our case to the state and, shared this vision and what we've done technically. And the timing was right. It seemed that this project aligned well with the state's goals. And they have provided or allocated $249 million to this project over the next 3 years. So we're hopeful all of that will come in the next 3 years, and that the state will stay as flush as it was this last year. That funding will get us into design in 2023. We're looking to design the whole system, and then move into our phase 1 of construction, which would be, we're focusing on getting the central plant built and a first phase of the project moving forward. And in the meantime, continuing to build out the financial package that we have. We'll stop there. Thanks.
Great. Thanks, Kira. Thanks for that overview. Yeah, I should just note, what I've observed at Berkeley. It takes a long time to do this planning, but Berkeley's leadership team is really behind this initiative. When we asked the campus for their highest priority capital needs from among deferred maintenance and seismic and all of the others, this energy project came to the top of the list, and that's what UC Berkeley advocated for. And so it's great that they've done enough planning to have this vision so that the state could provide the funding. So having the planning and the leadership support is really a key element for success here. Thank you. Let's move on to Brian Pratt, who is the campus architect and associate vice chancellor for design and construction services at the University of California, Irvine. We're going to hear, we've kind of gone through a project that was done, Kira's, which is in progress, and Brian's going to talk about the future with an all-electric hospital. Brian, over the past 8 years at Irvine, he's overseen a wide range of projects, including research facilities, laboratories, active learning classrooms, dorms, and other highly technical projects. He formerly has worked in both the private and public sector, and he served on the board of directors and as president of the American Institute for Architects in Orange County. He's a graduate of Cal Poly San Luis Obispo. I'll turn it over to you, Brian.
Thanks, David. Inspiring to be here. Thanks for having me, and I'm really thrilled to share some of our progress on our all-electric hospital. So a little background here: our hospital project site is on what we call our North Campus, which is about 1.5 miles from the main campus on the corner of Jamboree and Campus Drive. The project sits right adjacent to a beautiful marsh, which we think is a real differentiator for wellness and connectivity to the outdoors. And the project is quite an initiative for UC Irvine. As some of you might know, we have another hospital in Orange, a 400-bed, and I'll get into some of the details about the program here. But it's basically $1 billion project for UC Irvine, so very important project for us, and one that is very impactful for our community partners as well. Today, I'm going to talk a little bit about I'm going to talk about planning and how we got to where we are. But as a little bit of a segue into this afternoon's sessions, I'm going to talk a little bit about execution too, because we are in construction and making progress on this project. So where did we start? Many of you know that UC has a really pretty robust and prescriptive sustainable practices guideline or policy, and we've incorporated that into our campus standards and in our bidding processes and that kind of thing. And in the context of this project, the policy outlines acute care hospital facilities need to outperform ASHRAE 90.1 2010 by at least 30%. So, a pretty high bar for us to meet on an acute care facility. So a little bit about the program. This is a 144-bed specialty hospital focused on neuroscience, cancer, orthospine, and digestive health. It's comprehensive. It has 12 operating rooms and PACU and recovery and prep and an emergency department. It is not a trauma center. Our hospital in Orange is a trauma center. So it also includes a comprehensive cancer and ambulatory care center, the Chow Family Comprehensive Cancer Center, which focuses on cancer treatment, but also has infusion bays and other 10 operating rooms and procedure rooms, labs and conference space and so on. The project is pretty large scale for us. In the upper right, there's a parking structure. Lower left is the ambulatory care center, and upper middle is the hospital project. And you can see its adjacency to the marsh in this image. Jamboree Road would be to the right. You know, we're really excited about you know, the connectivity to the outdoors and some of the initiatives we're pushing forward, including LEED. And obviously, I'm not going to go through all the details of a LEED scorecard, but for the hospital tower, we are going to be LEED Platinum, which is terrific. For the ambulatory care center, central utility plant, and parking structure, we're going to be LEED Gold. And the reason for that is the ACC does not fall into the hospital category for LEED. And, you know, as you might imagine, it's very energy intensive. So it makes LEED Platinum pretty far to reach. So how about our all electric design? So we started with humble beginnings for all electric efforts. We started at Anza Borrego, a research station out in Anza Borrego Desert. And the HVAC and heat plumbing pumps are commercial grade packaged equipment, readily available, and results in a lower construction cost compared to a gas electric solution. The individual little hotel style living units are equipped with hotel style heat pumps. And in this case, going all electric resulted in lower first costs because underground piping distribution to the three buildings was not required, and a propane tank, concrete pad, and propane truck filling area were not required. Energy operating costs for the all electric heat pump solution is higher operating costs as the HVAC heat pumps operate in the winter months. However, the project includes a solar PV array to offset those annual energy costs. The project was really well received by the users, and they're very proud of their two LEED Gold buildings. So our first large scale all electric building is our continuing education building. This is a 5-story, 70,000 gross square feet cast in place concrete structure. And we deliver our projects design build. And so the design builders are really motivated to innovate and provide us enhancements in order to win the project. And so some of the enhancements included is a cast in place concrete structure with high energy performance, this beautiful courtyard on the right hand side with photovoltaic array shading it, and then an HVAC system that outperforms Title 24 by 24.7%. So this project is located kind of across a main street from our core campus, and it's beyond the district cooling and heating system distribution. So during programming, we evaluated the cost of extending the campus utilities to the building site, but the cost was prohibitive. So we asked for, in our DPP, detailed project program criteria, for a high performance, high efficiency standalone building. We listed energy goals for the project, but they were performance based, not prescriptive. And so that allowed the team to innovate and be more creative. So construction cost appears to be compatible with the gas electric design. We used a VRF system that has distributed refrigerated piping in lieu of duct mains and risers. No vertical shafts or fire smoke dampers for this system. and equipment, structural loads, and space on the roof is reduced with VRF system. The classroom heat pump air handlers are only slightly more expensive, and so we're tracking very well with that. Sorry, my notes are. Here we go. Sorry. So there are no gas-fired water heaters or boilers, and no site or building gas piping. Operating costs are lower, and you know, it really set the stage for our hospital project. So before UC established the new policy, they produced a study that came to the conclusion that all electric buildings are comparable or slightly less expensive than gas electric. And the study included a comparison of construction costs and operating costs for academic, residential, and lab buildings. So as we met with programming, architecture, and engineering firms, there have been mixed reactions to this, to construction cost assessment of the study, with some consultants suggesting all electric will likely increase costs significantly. So that was a kind of a daunting situation for our all electric hospital. We delivered design build, and so our some of the detailed pricing is not always available, but it seems that the study is so far pretty accurate in its cost assessments. But the hospital project energy cost for all electric is currently being developed, may likely result in higher operating costs than gas electric design. The essence of the new policy is that natural gas cannot be used for building and domestic water heating unless the new building is connected to an existing central utility plant. So not connecting to a central utility plant will require some form of electric heating. So this slide is a comparison of conventional gas-fired central plant with new hospital all-electric central plant. The goal is to omit conventional central plant natural gas reliance. The all-electric design introduces two types of chillers: heat recovery chiller plus air source heat pump chillers, to replace the conventional gas-fired boilers. These chillers reject their heat into the building heating system instead of sending it to conventional cooling towers. The third hospital chiller on top is a conventional high-performance chiller connected to a cooling tower, serves the high summer cooling load requirements of the new hospital. Electric steam humidifiers replace the conventional gas-fired steam boiler typically found in hospital environments, and the electric steam generators integral to autoclaves replaces the conventional gas-fired steam boiler source. So the coefficient of performance, a higher COP means higher energy efficiency, and heat recovery chillers have a high COP as the useful output includes both the cooling and the heating energy. COP for heat pumps in mild Southern California climates is a rule of thumb of about 3, so 1 unit of energy input and 3 units of energy output. The little photo in the corner there is of the domestic hot air source heat water heater heat pump. Shows the ductwork outside ambient air, and UCI has used this style really quite effectively. So the upper left shows a conventional chiller with a cooling tower, handles heavy cooling loads. Below that are the heat recovery chillers showing hot water pumped into the building heating system. The air source heat pump chillers provide heating water in the winter when chilled water demand is low. Annual chiller load may drop in the winter to 5% of the peak load, so air source heat pump chillers are required in the winter to provide heating. The chillers are robust, reliable, and redundant, and the design build team has put a lot of effort into coming up with the design for this approach. So the EUI, site EUI is building energy, source EUI, total energy, including the central plant. The top table is the Department of Energy benchmarks, and the proposed project EUI numbers are well lower than the DOE benchmarks and meet the UC sustainable policy targets. The carbon reduction number of 530 tons is a preliminary number, not yet finalized, but calced annual kilowatt hour reduction multiplied by a factor of pounds of carbon per kilowatt hour. So I'd like to conclude with this quote. UCI professors Molina and Rowland received a 1995 Nobel Peace Prize for the work in the 70s on identifying the ozone depletion of CFC refrigerants and propellants. This work was the basis for the Montreal Protocol for substances that deplete the ozone. UCI Chancellor Cicerone was also the head of the National Academy of Sciences for 11 years, where he influenced regulations and provided independent scientific advice to the nation. The UC system has benefited in its atmospheric policies by its own industry leaders. And I think this quote is particularly relevant today as we look forward to the future of all electric on our campuses. So with that, I'll finish up and turn it back over to David.
Thanks, Brian. Really want to thank you for all of your leadership. You know, some of the biggest challenges in electrification have been in the health system for UC, and having this project on the books and approved by the regents was really a milestone for everyone. So when other locations said it can't be done, we just point to Irvine and say, well, look what they figured out. So we really appreciate the leadership that you've been providing there. We've got lots of good questions. I think hopefully the speakers have been looking at them and preparing, but I'll read through them. First, for Gerry, we've got a few rapid fire questions about your heat recovery chillers. First, Carol asked, what temperature do your heat recovery chillers produce?
We produce 160 degrees is our typical value. We can vary that a little bit, but that's the target.
Okay, and are there time periods where there's not enough cooling for you to run the heat recovery chillers? And does storage carry you through, and can you run them as more as conventional chillers?
So in the peak of summer and in the peak of winter, we can't run the HRCs as much as we'd like. And that's just because we don't have the cooling to match the heating. We knew that going into it, and our next step is going to be, I think this addresses a future question too. We've already got a design ready to do some lake water heat exchange. And we want to do that in conjunction with some capital work we're doing with our non-potable irrigation underground system. So we're hoping we can load those up more during the peak with some lake water heat exchange.
Thanks. And I think this question was also for you. Questions about steam production for the med centers / hospital, and whether or not those health systems are included in your graphs.
So we have an adult hospital and children's hospital. They have their own greenhouse gas reporting boundary. For steam, how should I say, for non-space heating steam requirements, that's still a challenge for us. We have a very small steam plant for supporting both labs and the hospitals for the process load. So that's a very important area for future innovation.
Great. Yeah, Brian, can you describe a little bit more about how you're providing sterilization? I think you touched on it, but.
Yeah, so sterilization for our hospital is, was a really hot topic to determine whether we could actually go all electric or not. We are doing it all electric, and across the board we're all electric except for the emergency generators. So it was a topic of deep discussion, trying to understand the implications and the resiliency of all electric, but that's what we came to.
Great, thanks. Okay, Kara, here's one for you. There's a question about is there a on-campus energy aggregate program? Can you put PV on one building and be sent to another? Maybe you can just describe how your behind the meter solar works there.
Sure. So we do have some solar systems on campus on the main campus, and they're interconnected at the building level first. But if there's excess power that the building can't use, it just goes out into our campus grid to serve other buildings. We're looking right now. We're under contract for some additional solar on the main campus, along with battery storage. And we're looking at how this newest system can work more like a microgrid for us than the other systems, which will go down when the power goes down on the grid. But we're working right now with our vendor to see if that newer solar system, which will be about 1.6 megawatts with the battery, might be able to help us in outages. And that's kind of the model we'll be looking at for future grid connections for solar.
Great, thanks, Gerry. Yeah, just to expand on that, to Taylor's question, most of our campuses are set up like Kira's, where they don't export any of the renewable power. It's all behind the meter. So you can effectively put a big solar array anywhere on the campus and have it serve any and all of the buildings, depending on how it's configured. Let's see. I think this one is also for you, Kira, but maybe others can weigh in as well. How do the campus bridge the gap between climate action planning and studies and actual program implementation and greenhouse gas reductions? Maybe I'll start with you, Kira, and Gerry, you can probably add to that.
It's a great question. And I think that's kind of where we're at right now. You laying out the vision and the targets of what you want for your climate action, or where you want to get with the energy, and then putting together the pieces of the puzzles and the studies that take you to implementation. So I described a little bit about what we're doing right now with technical studies. So a series of technical studies, financial studies, electrical studies, the master planning that we've done, study after study after study, which you kind of have to put these pieces of the puzzle together, and then, moving into the project implementation. So what we're trying to do is position ourselves so that in this next year, we can, even though we may be building out the project in phases, that we're going to try and do as much of the design up front, so that when the funding becomes available, we'll be able to move forward more quickly in through the final design and construction.
Thanks. And Gerry, maybe tell us, you got it over the hump. How did you manage that transition?
Boy, it's a cliche to say you got to get the whole team involved, right? But I think one thing that made a difference is we were able to combine multiple needs. Like, there was a clear and present need for capital renewal, right? Most folks are looking at, how do I retrofit my systems, or how do I add to my systems? We had this nice clean break where we had to do something new. So you get people who need to do that. We were also just happened to be doing sustainability master planning at the same time. And I think there, again, it's better to be lucky than good. I think we had the right staff at the right time, both university leadership who are very, tangible focused on physical things, and we had good operation leadership here. So luck was a good part of it too. But try to, bring together multiple drivers, because it's hard to get everybody around one idea, right? There's got to be some fingers in there for everybody.
Thanks.
And I would just add to that, what Gerry said in terms of, bringing everybody together. One thing that we've learned is our design partners are very innovative, and many of them are, really at the leading edge of some of these conversations. And so if we put forth the challenge, they often rise to the challenge. And having them as partners can really advance the initiatives and help bridge that gap.
Great, thanks for that, Ryan. Kira, yeah, you mentioned the partnership with faculty on the borehole study, and Paul's asking a question about what are the outcomes to date? Was geothermal heat source considered a viable solution?
Great. I have not seen the in-depth analysis. I think it's going on now. What I have heard is that the soils look promising for us, and that they're, from the researcher standpoint, enough potential for us to look at it that we are going into a next phase of study. We're going to do a second borehole on the site where we're going to be putting the central plant, where we might be able to do boreholes and study out a portion of the campus that we think will be in our first phases of connection to the thermal system that could benefit from the geothermal heat exchange. There's still evaluation going on how some early of the evaluation is showing that it could really benefit in terms of electrical savings, but we're also hearing that we may actually see more benefit with water savings associated with the system. So, yeah.
Great, thanks. We have I guess a kind of a general question about the cost of building new infrastructure and piping to achieve electrification. I think maybe you covered the general topic, but Gerry, just what do you put as your total cost for your campus electrification effort? And then Kira, I'll ask you to give the same total.
Yeah, I'm not involved with new construction, but I can tell you our project costs almost $500 million. And, Stanford, 14 million square feet, and apply those numbers. I'm sure it would be dramatically higher, probably at least 50% higher if we were doing it now. And then because we have this infrastructure, we can take advantage. There's really no impact to new construction. Unless we're talking about, electrifying in-house steam and things like that.
Yeah. And Kira, what's your current planning number?
Probably similar to what Gerry described for the core thermal system and the distribution. It's difficult. We're hearing it's difficult right now from our costing consultants because of what's happening right now in terms of supply chain and construction costs are about 20% higher now than they were a few years ago. So, it's like Stanford times seem like good times now when we're thinking about what we're doing next. But we should have a better picture of that costing in the next 3 months as we finish the planning process we're in. And this is just the capital. So we're also looking at it from the life cycle perspective, and then also how much, trying to balance how quickly we would be the benefits of phasing in all of the buildings as soon as possible so that we're not running two systems for a long period of time while we're doing the transition. So we really kind of need to look at the life cycle costs and the commodities and look at that full picture.
Got it. Here's an interesting question, probably for Gerry and Kira. I think I know the answer, but are there plans for recycling your end-of-life boilers or cogen equipment? Gerry, what did you end up doing with that stuff, and what are your plans?
Yeah, I can tell you what we did. Fortunately, a lot of things were end of life, so it minimized our stranded assets, but there still were millions and millions of dollars of stranded assets. We put it in the general contractor's scope that they had to scrap everything out as they tore it down. They actually found someone to buy the old GE turbine, which I don't know if that's a good thing or not. Maybe it should have been scrapped, but there are markets for some of these things. I think like most folks, our boilers were 70+ years old, so I think those went straight to scrap metal. Most of our chillers were pretty old as well, and so I think again most of these things went to scrap. Just a responsible removal. But yeah, if we had newer systems, I don't know. I guess Kira's really looking at this now, right? You got to make those decisions.
Yeah, I would just add, I think it's going to be similar for us in terms of the cogeneration plant and the systems that the equipment will be old. We just put in a new turbine for the cogeneration plant, but that plant will, it's got a 5-year plus life on it. We'll probably be using it through the transition and the construction that we're doing. We are looking a little bit about at larger cooling systems that we have on some of our large buildings, and how they wouldn't be used as primary sources for the new thermal plant, but how we can use that to support the transition period and as backup so that we're not stranding some of those new assets. And we're going through a process right now of looking at what's coming online in terms of new construction and large renovations and advising about the least cost solution we can have to ready those buildings for a transition to hot water so that we're not building out expensive HVAC systems that we're not going to need.
Thanks. Okay, now we have a question about resiliency, and this is an important topic that comes up whenever we talk about electrification. Maybe we'll start with you, Brian. Discussion about resiliency in the future as we become more dependent on the grid for our low carbon electricity. How did that work into your plans, and what are your
I think that's a super important question. So, we're fortunate where we are and where our hospital is to have, really quite reliable power, but we're served by Southern California Edison, and they have great aspirations for providing, green power, and the problem is they're struggling to keep up, and so there was a lot of discussion with Edison going into the planning of our hospital to gain the confidence that that an acute care hospital is going to be safe and up and running, for years to come without issue. Of course, there are all the emergency backups and everything, but a great deal of conversation with Southern California Edison about their capability on the infrastructure side to support, a very vital kind of project. So a lot of discussion in advance of making the decision to go all electric.
Great, thanks. And Gerry, what's your experience been? Was shutting down your own power plant was probably a big issue for you as well. How has it worked out?
Well, a dirty little secret was we never island with our cogen, and technically it was possible, but we never did it. And the times we thought about doing it, well before we could even get it started, the grid was back. And at that scale, it's not as easy as possible, the steps that have to go in to sync things up. Now, we're so heavily dependent upon the grid, it is a concern. But we also see it as kind of a community responsibility, right? I mean, it shouldn't just be Stanford with reliable power. I mean, we're all in this together. We're co-located with some hospitals, so similar benefit to UCI. But we're always working with PG&E. It's how do we harden what's coming in. In parallel, we have to look, what do we do on campus during emergencies? Because emergencies will happen. And how do we do that smarter? Just dropping in more backup generators is a pretty crude way, and even that's not perfect. You find a lot of imperfection there. And so this is where you get into really applied smart grid, right? What is smart grid? I don't really know, but if we could come up with a way to use fewer assets to provide more resilient backup on campus, we want to do that. So I see it as a big combination of active demand management, highly controlled isolation, as opposed to just shutting, killing a building completely. What are things that we can do with our smart controls now where we can start isolating loads so that you can keep maybe a critical part of a building up and running? We set targets for ourselves, how would we go from 50 megawatts down to 25? And we do that thought exercise. How do we do this? What combination of things? And so I think this is where we will start to see adoption of batteries. You're going to get a co-benefit with batteries, not just, renewable ingestion, but part of the resilience. So I see a lot more research in this area, and it's not going to be any one thing, but there will be some code running, right? There will be some optimization happening to help smooth out these emergencies.
Yeah, that's great. I like your point about you were never set up to island, because I think that's the key. Resiliency has become a real important topic, but most of UC's cogen plants weren't really designed initially with islanding as the primary goal. Some were, some aren't.
And I guess the implication I didn't mention is, in the old days, if the grid went down, the cogen went down because they were synced and they had to, go down together.
Yeah. Okay, let's see. Maybe this is one for everybody. Basically, questions about lessons learned with the status of your project so far. There's things you wish you would have done differently. Maybe I'll start with you, Kira, and then go into Brian.
Sure. I think one area would be to have approached the land use discussion a little bit differently. It's, we're a pretty built out, congested campus. We were very much excited about a distributed plant concept at first, and trying to combine the plant construction with new construction going on with buildings or others. And we found over time that we really needed to decouple the energy project from other projects on campus, and that locating a piece of property. So that's just one piece of it. I think although we started in 2015 and it took us several years to get to we're going to the electrified solution, I think we still needed that time. It wasn't wasted time. It was really building that building the discussions on campus and the community that we needed to make this transition, and that it was real.
And hey, Kira, there's a quick follow-up question about Berkeley. Have you considered, back to resiliency, considering keeping the gas turbine as a source of backup power?
We are looking at that opportunity, and there's a couple of scenarios that we're looking at. There's some challenges from an operational standpoint to keep it operating. We almost have to keep the whole operations in place, even if we're using it for emergency services. And so we're kind of grappling through that now. I think we'll be using that asset in some way. I'm just not sure how and for how long. But great question, and love to hear from other people that have used that, made that transition and used that solution for backup power.
Yeah. We'll circle back to you, Brian. Any things you wish you'd done differently so far?
I think we're pretty confident so far. Just going back to that resiliency piece, I think, working with Southern California Edison, as another, large public agency, presents some challenges just in terms of things like turnover of people. You start conversations years in advance, and then later in the project you're tracking with other people on their side of the table. And so I think lessons learned is really clear decision making years in advance with Edison, but also really good documentation and communication, ongoing communication as they kind of change folks on their side of the table and that kind of thing. But I just go back to that resiliency piece because it's so important. Having the confidence that Southern California Edison is going to be there for us through thick and thin is really important and a big part of our partnership with them.
Yeah. Thanks, Brian. Yeah, our utility partners are on the line here, so I want to reemphasize that we need a safe, reliable grid to make this transition happen. And I view it as in terms of our support and kind of a climate justice issue, we can't just be the ones that keep the lights on because we have our own power plants. We need a grid that's serving everybody during these crises, and we can help lead that transition. But Gerry, back to you. Any things you wish you'd done differently?
Well, I'll get down in the technical weeds here a little bit, just as I can. I think at a macro level, I can say our chilled water demand has grown on campus faster than we forecasted, and we knew it would grow. So, make of that as you will. We had planned for expansion in our plants, in our systems, but we're using up that expansion, at least 5 years sooner than we thought we would. So, when you're doing your forecasting models, it's going to get hotter, but sometimes there's some additional implications. So your existing campus may use more cooling, but what happens when you start retrofitting things like maybe some dormitories that, like in the Bay Area, they weren't historically air condition. What happens if you have to start air conditioning now? So suddenly there's new square footage that needs to get added. So make sure you're right sizing for 10, 20 years out, and there could be a little different combination. The other thing, down in the weeds, and if for anybody who is looking to do, building level conversions from steam to hot water, the old industry rules of thumb and how you get energy to a building with steam, completely different than with hot water. And we had a lot of surprises and a lot of narrow misses, and some things we had to go back and redesign and fix just because, getting the right amount of water to the right place through the right heat exchanger, there was a lot of surprises there. So it seems simple, but make sure you do your basic mechanical engineering, because it is different. We take for granted that hundreds of years of human engineering experience around moving steam, and you just take for granted that you just know how to do things. Outside of chilled water distribution, we don't have the same, certainly in North America, that same experience moving around utility hot water. There are some gotchas in there worth looking out for.
Great. Thanks, Gerry. We have quite a few other technical questions in the chat. I think we're out of time to go through those, but I think our panelists will get a copy of this and they can provide some responses perhaps after the fact. But in our last minute, I'll just give you all 20 seconds each for any closing thoughts, starting with you, Kira.
Thanks. This is an exciting journey. It's worth it. It's overwhelming. Get your teams together, get your support structure. It's a journey, but it's worth it. And looking forward to seeing a lot of us doing this in the future.
Brian?
Yeah, so inspiring to be here. Thank you for having me. Great questions too. I think one of the things I think is a takeaway is that notion of using your teams as a resource, your industry partners as a resource, because there's incredible innovation out there, and pushing challenges out to your teams results in pretty amazing things, and you really can gain some momentum behind some of these initiatives. So use your teams and resources and outside industry partners as a resource.
And last word, Gerry.
Yeah, I'm looking forward to y'all leapfrogging us, because you're already working on some issues that we don't know what to do with, and we want to start copying you. And that's, I think, what we do here, right? We always take it one step further, and I look forward to catching up.
Thanks, Gerry. Okay, let's have a round of applause for our speakers. Thank you so much. And I'll turn it back to you, Davis.